Okay, it has begun the recording now. So we are assuming that species 1 reaches a carrying capacity K1 in the absence of species 2, and we can write that in the following form. Is that correct? Okay, likewise, species 2 also reaches a carrying capacity K2, whose intrinsic growth rate is R2, in the following form. Okay, so these are the equations when species 1 and 2 are on their own in the absence of the other. Now, how do we incorporate competition between them? Okay, so this we call intra-specific competition as well. Okay, so how do we incorporate that? Basically, there has to be some additional depth, right? Additional growth rate that captures inter-specific competition. Can say this is reduced growth rate or increased depth due to interspecific competition. Okay, likewise same here. Okay, now how do we go about doing that? The simplest way of doing it is the following. Okay, so you remember what we did? We wrote down, when we wrote down equations for competition within the same species, which is also called the conspecific competition, what did we do? We wrote that, we did this, right? We assume that the per capita growth rate of species 1 okay, this decreases with n1, right? This was the assumption we made to write down intra-specific competition. So this was so likewise, can we think of writing a graph that represents interspecific competition? How would this look like? So, writing this gave us this form of logistic, continuous time logistic model, right? So if you do the same thing now for species, the competition because of other species, what should be the y-axis? What should be the x-axis? Let's think of what y-axis.
Y-axis can be the same and the x-axis can be N2.
Exactly. So y-axis, because I'm still interested in writing an equation for N1, of course, we can do N2 later on. And then now we want to know the effect of N2 on this, right? And when N2 is 0, what do we think should happen? This per capita growth, let's say, for whatever we are doing this for some value of, some given value of N1, it will be some value here, right? There is some growth rate which is in the absence of N2. Now, as N2 increases, what should happen?
It should reduce, right?
It should reduce. So again, the simplest model is to assume that it reduces in a linear way, right? So we can apply the exact same principle here. Okay. And then we can write down the equation as follows. Okay. So I'm going to use the sort of notations used in this book. Largely, not entirely, because I know, I think it's chapter 5 has something is called competition. Okay. So do read it because it's really nicely written. It sort of very nicely discusses how each mathematical term must be interpreted and so on. It does in a very, very nice job, in a nice way, and also an accessible way. So I encourage you to read that book, not just for this, but in general. Okay. So now, so let's write down in the following way. Dt. Okay. K1 minus N1 minus alpha N2 divided by K1. Okay. So I'm going to write this as, so just so that we remember what is alpha, I'm going to write alpha 2, 1. Why am I writing it as 2, 1? It's the effect of competition because of 2 on 1. So 2, 1 means I'm using that to mean that the competition goes in the direction 2 to 1. Is that fine? Okay, I hope that the books don't use the exact opposite notation. It's actually possible that some books do, but this is what I am, so think of it as f, sorry, 2, 1 effect of competition of species 2 on species 1. Okay, and likewise you can invert the definition. Is this fine? So this is basically, this means that for a given n1, all else being equal, how will the per capita growth rate of n1 reduce now? It is decreasing linearly with n2. That's what we have captured, right? Okay. Is this fine? Okay, so now we can write down an exact, very similar equation for now n2, just following exactly same steps. So rate of change of population 2 is R2 K2 minus n2 minus alpha 1 2 n1 divided by K2. Is that fine? Likewise, alpha 1 2 follows. It's the effect of competition of species with species 1 on species 2. Okay. I think Gottel uses alpha and beta, but I prefer this to for us to remind ourselves what exactly is the direction of competition. Yes. Are the equations fine? Okay, these are called Lotka-Volterra competition model. This is called a Lotka-Volterra competition. Okay, any questions on the model building aspect? Do you all feel comfortable in thinking about writing these kind of equations now?
I have a doubt.
Yeah.
So if we like see the term for the N2, so there that contributes always negative to this per capita rate, right? There is always a negative contribution.
Which one? Sorry, where is which
The-
term are you referring to?
This for the population N1.
For the population N2, for the population N1, N2 acts negatively because there is competition. Yes.
So in the graph that you have made, so there for some value less than say N2, there is a positive contribution.
No, it's not a positive. So presence of N2 is decreasing its baseline growth rate. No.
Okay,
It's
so
not a
you are
positive
talking about
contribution.
overall.
It's not a positive contribution. No, that's not what it is, right? Okay. It's actually decrease in the DN. So basically, one way to think about this is, if I were to separate this entire this term into two parts. The first part will be K1 minus N1 divided by K1 minus alpha 2 1 N2 by K1. Okay.
Yes.
Okay. So for a given value of N1, when N2 was 0, what's the value of the per capita growth? It will be K1 minus N1 divided by K1, right? That's this value going to that will be this value. Adding any value of N2, however small it might be, is reducing it, right?
Oh, okay.
It's always negative. So it's not a positive contribution. Okay, it's a good point you asked, but it's not a positive contribution.
Yes.
Any other questions on the model part? It's useful to clarify these kind of doubts. Very important.
So the slope of the line on the second part on the right side will be
Mhm.
alpha 2 1 by k1.
Yeah. Must be.
Okay.
I mean, there's also an R1 there. So it will be R1 alpha 2 1 by K.
Okay. Okay.
Negative slope minus R1 alpha 2 1 by K1. Yeah. So if you want to make an exact association with this, the value here, so 1 over n dn by dt at n2 equal to 0 is equal to basically R1 times K1 minus N1 by K1. That's this value here, okay? And then the slope, as you rightly said. So let's write down 2 points here. A is this. The slope of the line will be minus R1 alpha 2 1 by K1. Yeah. If you refer to other books, they may write the model in slightly different, with different coefficients, but the model still is same, has the same structure. Okay. For example, in some books you may find that this term is basically added directly in the form of this. Okay, 2 1 and 1 and 2. Okay, so they may also do this in some books. Okay, so but I have just done it this way following the Gotari. It just makes some interpretations a bit easier. So in some sense, so here our alpha has some element of k in it, whereas this is completely exclusive. But those small differences does make a problem in our interpretation. Okay, but let's call alpha prime to distinguish this our alpha. Any other questions? Okay, so if there are no questions, I'll start analyzing this now. Okay, so now how do we analyze this? So far we have learned how to analyze a model of this type, right? If we had, if for a single species, if we had dn by dt is equal to f of n, we knew how to analyze. What was the principles for analysis? Equilibrium were given by f of n star is equal to 0, right? And the stability was given by f prime n star, the sign of this. If it is less than 0, means n star stable. So this is what we know from a single species population model. Now we have something more. So we have two species model. Okay. So if the general form is this, so the growth rate with the growth rate of n1, okay, can depend on both n1 and n2 now, right? In our case, n2 basically causes decline in the growth rate. Okay. And then if we have a second species, its growth rate, which I am denoting by n2, also depends on n1 and n2. Right? So this is the general form of interacting species system. Okay. In fact, this form is also applicable for predation and competition, and other types of systems. Okay. So now, how do we define equilibrium now? For this system, how do we define equilibrium?
Where both are zeros. Both.
Exactly. So equilibrium, remember what does equilibrium mean? Equilibrium means that no dynamical variable changes. Therefore, both dn1 by dt and dn2 by dt are 0. Therefore, you find equilibrium by simultaneously solving these two equations. Okay, so this is how you solve the equilibrium. What about stability? Okay, stability for this becomes relatively more complex. So to know the stability, we need to do a bunch of steps. We need to calculate a matrix called a Jacobian matrix, which is given by this. So I'm not going to derive this. The proof for this will be available in any most standard books. Okay, so what are we doing here? We are calculating the derivative of f1 partially with respect to n1. That becomes the first term of your Jacobian matrix. And then you calculate derivative of, oh, sorry, this should be f1. No, again, the same function with respect to n2. Those become the first row of your Jacobian matrix. And likewise, the second row comes from taking the derivative of the second growth rate function with respect to n1 and n2. And then you calculate this matrix at the equilibrium values. So earlier we were calculating the derivative of one function at the equilibrium value. We now calculate the Jacobian matrix at the equilibrium. Having done that, what you now need to do is find the eigenvalues. Let us denote them by λ1 and λ2. Then find the eigenvalues of the Jacobian matrix. Okay. And if the real part of λ1 and real part of λ2 are both less than 0, you have a stable equilibrium. So for proof, please refer to, I think it's there in, we'll find this in many books, but maybe in the books that I have recommended, you can look at chapter 5 of Stogads. I think it's there in 4 or 5, but I think 5 is the right chapter. Yeah, that's what it is. Okay. So any questions on this? Okay. So now let's go to the, let's apply these principles to the Lotka-Volterra competition model, except that we will not use this way of finding stability. We will do it entirely using the graphical methods. You remember the graphical methods we did for, one species dynamics. We'll use the analogous method. So before we do, let's find out what are the equilibrium. So what are the equilibrium values for the Lotka-Volterra competition model? Okay, let's look at the most obvious equilibrium. So basically, what we basically discovered was, both of these must be simultaneously 0. Okay. So what is the most obvious equilibrium possible now? One possible equilibrium is that both n1 and n2 are not present in the system. See, if I set n1 to 0, right, this entire right-hand side equation becomes 0. If I set n2 to 0, growth rate of populations 2 also becomes 0. So one way to achieve both the populations growth rate to 0 is I set both n1 and n2 to 0. Okay, that means there are no species. Okay, which is obviously what we call a trivial solution. Okay, that's one equilibrium. The second equilibrium, again, think of the one extreme. There are 2 species possible, right? Okay, there are 2 species that are competing. Just think of what are the intuitively possible outcomes.
One
One-
species zero, the other species
Yeah.
has the carrying
So
capacity.
which is basically, only when one of the species is present, right? So now let's say N2 is 0. Okay. Let's say if N2 is 0, okay. So in this equation, right, the second equation now becomes 0, right? Second species is absent. And what happens to the equation above? N2 is 0. See, we don't want to consider N1 0 because we have already done that again. So let's leave aside the first R1 N1 term. If we want this term, the term in the bracket to be 0. Okay. How can the term in bracket to be 0 now? N2 is anyway 0. So therefore, we just have K1 minus N1 divided by K1. And the way that can be 0 is when N1 is equal to K1. So basically, intuitively, this just corresponds to the fact that species 2 is absent and species 1 is at its carrying capacity, K1. So this is 1, and there is a comma. Okay. K1, 0. So what's the inverse of this?
0, K2.
Species 1 is absent and species 2 is present at its carrying capacity. Okay. Now, what is the fourth possible equilibrium? So let's also write down what does this mean verbally. This means that both species are extinct. Only species 1 present. Only species 2. So what's the fourth possibility? Thinking about this again mathematically, there are two terms in the first equation, R1 and N1, that can be 0, or this term in the bracket can be 0. Likewise, we have, the R2 N2 term that can be 0, or the second bracket term can be 0, right? So basically, there are two ways the first equation can be 0. There are two ways the second equation can be 0. So there are basically 2 into 2, 4 possibilities. We have explored this possibility, and this possibility. The fourth possibility is when the bracket terms are both 0. N1 and N2 are not 0 on their own, but the terms in the brackets are 0. Okay, those are called the coexistence equilibrium. So this will be the coexistence equilibrium. Now this requires some algebra. Okay, so how do we do this? We set, so what does it mean when we say that the bracket term is 0? The numerator is 0, right? So we have to do some algebra here. So numerator is 0 when K1 minus N1 minus alpha to 1 N2 is equal to 0. Likewise, the second bracket term is 0 when K2 minus N2 minus alpha 1 to N1 is equal to 0. Now we need to solve these two simultaneously. These are basically two simple linear equations. You can solve them, using your high school algebra. And so I won't do the algebra now, I think. Okay, I'll just try to see if you can just write it down. I hope you can verify this when you have time. So just think about this intuitively if it makes sense. So N1, because N2 is present, it has to be less than K1, right? Same denominator. So these are the N1 and N2 stars for the coexistence equilibrium. Remember that when both of them are present, they are both present at values which are less than their own carrying capacities. Okay, that's not necessarily very evident because you are also dividing it by this denominator here, right? Okay, but it's possible to show that indeed that's the case. Okay. Okay, any questions on this? How we have found the equilibrium for both the species now for this simple model? Okay, so if there are no questions, I will go to the page 3 now. Now, how do we look at the stability of this? Okay, so the stability of this, the strategy is as follows. We know the two equilibria now. The idea for stability is to plot what is on this N1 versus N2 axis, what are the basically growth rates? Okay, so if I know the growth rate at every point in this space N1 comma N1 N2 space, wherever the growth rates are 0, those will correspond to equilibrium. Do you agree with that? Okay, and looking at the overall flow, the growth rates in this N1 N2 state space, we will know whether such an equilibrium is stable or unstable. This is exactly analogous to what we did with one-dimensional case. The one-dimensional case was basically this, right? We were plotting f as a function of n, and we will look at what different n's, what is the growth rate. The challenge here is we have N1 and N2, and we have F1 and F2 functions. So it's a much more complex. I know, it's a much more, it's at least a three-dimensional representation, okay, which is a bit hard, but it's possible to do something with this. So basic idea is to plot something called null clines, or something also called isoclines. So null clines basically are the lines where null clines for species 1 follow this, and null clines for species 1 follow this. Species 2 follow this. Okay, so let us see what is an null cline for species 1. Remember, the species 1 or dn1 by dt was basically product of this term with this term, right? So when will dn1 by dt be 0? When this term is 0, or when this term is 0. So basically now both of them independently form the null clines of species 1. Okay, so I will now write down. So the null clines are R1 N1 is equal to 0. That's the first null cline. Second null cline is K1 minus N1 minus alpha 21 N2 divided by K1 is irrelevant. That's equal to 0. So these are two null clines corresponding to species 1. Shall we plot them now? I'm going to use blue colors to plot null clines for species 1. Okay. And I'm going to use red color for the species 2. So what is R1 N1 is equal to 0 mean? It just basically means N1 is equal to 0. It basically means N1 is equal to 0 is basically the y-axis. So I'm plotting it very close to y-axis. Okay, but this is really N1 is equal to 0. This is the first null cline. Let me call this 1. Let me call this 2. So this is 1. So what is the second null cline? It's basically I can write it in the following way. I can write this as N2 is equal to K1 minus N1 divided by alpha 2, 1. Is that right? Can simplify this equation to this. This is the null line for second null line for the first species. Okay, so which means when N1 is 0, you have K1 by alpha 2, 1. So there is some value here which is K1 by alpha 2, 1. That's K1. And then it again, it is when does N2 become 0? N2 becomes 0 when N1 is K1. So it's K1. And it's basically a straight line that connects these two. Oh, sorry. Wherever it hits 0 becomes the K1, okay? Okay. So this value is K1. Okay, is this fine so far? I have plotted two null lines, both of them corresponding to species 1. Any questions on this? Okay, no questions. So let us now then plot the null lines for species 2. Okay, what are those going to be? Those will be R2 N2 is equal to 0. That's the equation 1. And then exactly the converse of this. This means that again, let's write this in the form of K2 minus alpha 1, 2, and 1 divided by, yeah, that's it, right? Yeah. Okay, these are the two null lines for species 2. Is that fine? So let's write down first null line for species 2. That's basically N2 is equal to 0. That's basically x-axis. Okay. What's the second null line? The second null line is N2 is equal to K2 minus alpha 1 to N1. So when N1 is 0, it's K2. Okay. So here is we have to now make some choices. So when N1 is 0, second null line has a value of K2. So where do I plot K2 here? Will K2 be here or will K2 be here? That's not clear, right? So I can now make a choice. Is K2 less than K1 divided by alpha 2, 1? Or is it more? Just let's arbitrarily right now choose K2 to be this. Okay. And then it goes on. And where does it hit where N2 becomes 0? When N1 is K2 by alpha 1, 2. Okay, this value is K. So this value is basically K2. Okay. And it meets it. There are now, this is straight line. Right? The straight line now again can have two form. One form is this, right? Other form is this. There are two ways. Are you able to see my cursor, by the way? One way is this, other way is this. Okay. And let me now arbitrarily choose that to be this way. Okay, so which means this is now K2 divided by alpha 1, 2. Okay. Is everything clear so far? So while drawing this, I have made two assumptions. The first assumption is that K2 is less than K1 by alpha to 1, because I wrote this below. And the another assumption I made was that K2 divided by, alpha 1, 2 is less than K1. So I made two assumptions to arrive at this graph. So any questions on this before we go further? It's basically simple graphing, by the way. Nothing very complicated. So everyone seems fine. So now from these graphs, how do you find equilibrium? So the way to find equilibrium from this is, wherever red and blue lines meet, that means that the null lines of N1 and N2 are meeting, right? And whenever both the null lines meet, that's precisely the point when the growth rates of both the species are 0. So therefore, to find the equilibrium on this graph, we must look at the intersection of null lines. Okay. So intersection of null lines, gives us equilibrium. Except that we have to look for intersections of null plane of species 1 with that of species 2. Okay. Okay, so let's look at identify them wherever red and blue lines meet, in simple words. So this is one equilibrium. This is another equilibrium. This is another equilibrium. So there are basically three equilibrium values. Did we miss anything? By the way, that these two blue and red lines need not be perfectly parallel. That's the way I have drawn them, but they don't have to be parallel. All that this means is that they don't intersect in this N1 N2 quadrant for the positive quadrant. Okay. Is everything fine so far? Okay.
The
Here is another
coexistence.
Say that again, sorry.
Sir, the coexistence equilibrium.
Equilibrium. What happened to that? So for the conditions that we have written out in this box here, from what can you conclude now? Is coexistence possible?
No.
So that's what this means. Yeah. So this graph tells you, but by the structure of this, coexistence is not even possible. Of course, you should think why, what's the intuition, what's the ecological intuition behind that? You should think about it. Okay, why that's not even allowed. So we'll just, I think if once we complete this, it will be clear. Okay. So here is the basic idea of how do we analyze these null lines. So I think I should have done one more small thing before I wrote down both the null lines. There is one very simple rule of thumb you can follow. Okay. Whenever you are below a null line, okay. Okay, whenever you are below, let's say, let's think of null line, this null line 2 of species 1. Okay, this 2 of species 1, right? If you are above this, what's happening? If you are above this, N1 and N2 are large. Is that right? If you are somewhere here, N1 and N2 are both large, right? Okay, now that means that this term, equation 2, basically becomes negative, right? When equation 2 becomes negative, what happens to dn by dn1 by dt? That becomes negative, right? Which means basically N1 and N2 are large, dn1 by dt becomes negative. Now let's look at the, which means that if I'm here, there is actually a pull back towards N1 has to reduce. in all these regions, because N1 and N2 are too large, therefore the growth rate of N1 is now negative. We can apply the same logic for N2. If N1 and N2 are both very large, this term is negative, therefore dN2 by dt is negative. So therefore, N2 has to reduce. N1 has to reduce, N2 has to reduce. So therefore, basically things are all flow, coming back broadly, as a net result is that, things are actually coming, reducing. Both N1 and N2 are reducing. Okay. So one general rule of thumb is that if you are above the null line, okay, at least for this model, if you're above the null line, the growth rate is negative for that species. Let us apply this rule for both the species. So when we are in this region where we are above both the blue and red null lines, both the species are reducing, and therefore you see a net flow in this direction, roughly in this direction. On the other hand, if you are below the null lines, both the species are very small in number. Therefore, both these terms in these brackets will be N1 and N2 are very small. Therefore, this term will be positive. So will this term be. Therefore, basically both of them are increasing. Both species 1 and species 2 are increasing in this region. But what happens in between blue and red? In between blue and red, you are below blue, which means that blue is increasing. There is a flow in this direction. But you are above red. What's happening to red? Sorry, blue is increasing. I'm going to do it this way. It's a very messy graph. Very sorry. I should have done a bigger graph, I think. What happens to the red, the species 2? Is it increasing or decreasing?
It's decreasing.
You are above the null line of species 2, which means the numbers are already too large. Therefore, this is reducing. So in this intermediate region, species 1 is still increasing, but species 2 is decreasing. What's the net effect? Net effect will be pushing in this direction. Okay. So basically what this means, if I'm here, I'm coming down. If I'm here, I'm going up. And if I'm in the intermediate region, there is a net push towards in this direction. So what can we conclude from all of this? That this equilibrium is a stable equilibrium. This is unstable. This is unstable. There's only one stable equilibrium, which corresponds to, so this condition corresponds to what? Species 1 outcompetes species 2 in this condition. In fact, the stable equilibrium for this condition is K1, 0. Do all of you agree with what I have just done? Any questions? I don't know if zooming in helps. It's a badly written graph, maybe it doesn't help. Okay. So what this basically is also called, the conditions that we have just written down also lead to. So this is what we can call case 1. Case 1 corresponds to K1 is greater than alpha 21 times K2, and K1 is also greater than K2 divided by alpha 1, 2. Under this condition, what happens? Species 1 competitively excludes species 2. Okay, so sort of just to think up, let's think about this sort of, in a crude way. So alpha 2-1 is the computation of 2 on 1, right? Is that fine? This is the computation of 2 on 1, and then you are multiplying it with the K2. What does it mean? Let's imagine that what is the worst case scenario for species 1? Worst case scenario for species 1 is species 2 is present and its carrying capacity. Is that right? Species 2 is present at carrying capacity. Okay. And therefore, what is the competitive effect of species 2 on 1? Go back to this equation. So this is the competitive effect of species 2 on 1, right? When is this maximum? It's maximum when N2 is K2. Only species 2 is present. Okay. What this condition basically means is that even when entire K1 is so large, the carrying capacity of species 1 is so large that the competitive effect, it actually sort of, is still better than the competitive effect of the species 2. Therefore, even when you introduce N1 in a very, very small quantity, this K1 minus alpha 2-1K is positive. Therefore, N1 can grow. Does it make sense? So this condition ensures that, the first condition ensures that even when the species 2 is present in carrying capacity, small introduction of species 1 can begin to grow. That's what the first condition means. What does second condition mean? Second condition means that carrying K1, maybe I think that it's better to think about this in the opposite way. Maybe I won't write it this way. Write this as K2 less than alpha 1 to K1. It's exactly the inverse of this, right? So when species 1 is fully present, then species 2 cannot invade. That's what this condition means. And when both, so the species 1 can invade even in its worst condition, but that's not true for species 2. And put these two together, you find that species 1 will competitively exclude species 2. Is this clear to everyone? Any questions? So because if you understand this correctly, you can write the conditions for the sort of converse of this very easily, right? When will species 2 competitively exclude species 1? That should be very easy to do, right? You just invert everything, all the signs, all the the species 1 and 2 interactions. So therefore, please understand this clearly. Ask me any questions. Any questions? Okay. Okay, if there are no questions, I will move forward. And so we can begin to write down now additional cases, right? So we can write down now case 2. Now again, think about it in a graph. I hope to write better graph now. Okay. N1, N2. Okay, let's write the blue lines. The blue lines we can always sort of keep them sort of fixed. So one is the N1 is equal to 0 null line. So other one is this null line where it hits here at K1, it hits here at K1 by alpha 2, 1. Okay, so an obvious converse to this is that this, the null line for the species 2 is now here. So you know, without, and I will leave this as an exercise to you, then what you will find is this equilibrium will become the stable with an outcome of, you know, basically species 2 competitively excludes species 1. Okay, so again, one can just write down now these conditions very intuitively, right? So K2 must be greater than alpha 1 to K1. Okay, which means that even when species 1 is present in its carrying capacity, you know, species 2 must be able to invade, and the converse of this is K1 must be less than alpha 2 1 K2. Okay, which means that when K2 is at its carrying capacity, K1 is unable to invade, and this condition forms species, you know, case 2. So other two equilibrium were this, but they are not stable. Okay. Now let's write down the next case. Case 3. N1, N2. So again, let's keep the blue null lines exactly as we have done. So this is K1, this is K, this is K1 by alpha. Okay, so what's the next possibility now? Of course, this will always be the same. This null line doesn't change. So what's the next possible scenario now? So remember that there were two things we have done so far. One where, you know, both these points are below blue line. The other where both these points are above the blue line. So now we can do two scenarios where we can start here, do this. Okay. So what is this, by the way? This will be K2. So this is K2, and this will be K2 by alpha 1, 2, if I'm right. Is it correct? Okay, excellent. Okay. So now what are the equilibrium now? So now let's mark all the equilibrium. So this case is a bit different. Okay. So we have one equilibrium. Remember that all the equilibriums are basically whenever blue and red lines intersect. This is another equilibrium. 2, this is a third equilibrium. And we have a fourth equilibrium. So somebody was missing, the equilibrium of coexistence. So now that actually is a, a positive value. It can exist, but let's see what is the stability. So we have to now again use those principles of, when you're above the null line for both of them will reduce. Okay, so the net result is both the populations are declining. Okay, and if you are below the null line of both, what happens? This is increasing, right? And this is increasing. And the net result is both the population, both the N1 and N2 are increasing. Okay, now where do they go? So that means this is unstable. The 0, 0 is always unstable because we have assumed that R1 and R2 are greater than 0, by the way. Otherwise, there is no point in doing all these calculations. Okay, otherwise extinction becomes equilibrium. Okay, so they're both increasing. Now, where will they go? There are 3 equilibrium that they can actually go, but where will they go? So it depends. So we have to look at what happens in these intermediate regions. So let's start with this intermediate region. In this region, blue is decreasing, but the red is increasing. So blue is decreasing, but the red is increasing, right? Because I'm below the red line because the red is increasing. Species 2 is increasing. The net effect is in this direction, which means that this is a stable equilibrium. System will flow towards that. Okay. Now, what happens in this region? In this region, I'm below blue, therefore blue is increasing. But I'm above red, which means the red is reducing. So the net flow will be in this direction, which means this is also a stable equilibrium. So consequently, this has to be unstable equilibrium, which means here coexistence is unstable. However, depending on where you start, you may reach either all species, all of them being species 1, or all of them being species 2. Okay, this is also called what we call founder effect. Or we also thought of this as founder effect means the initial population size matters where the system will eventually go. Okay. So now let's write down the conditions for this. What is the condition for this? K2 is greater than K2 is greater than K1 divided by alpha to 1, which means that K2 K1 is less than alpha to 1 times K2. So what this means is that if the system is completely with species 2 at carrying capacity, then the carrying then basically species 1 will therefore lose out. So whenever species 2 is in a large number, basically this means that species 1 will lose out. That's the first part of the condition here. So likewise, the exactly converse must also be true, right? Based on what we have seen. The next condition is this dot is less than this green dot. Therefore, K2 by alpha 1, 2 is less than K1. This means that K2 is less than alpha 1 to K1. Meaning that the competitive effects of 2 on 1 is 1 on 2 is high, and that of 2 on 1 is high. Therefore, in some sense, both of them are actually competitive. So therefore, whoever starts first will have the advantage. Have competitive advantage when in large number. So this leads to founder effect. Okay. Any questions on this? So I will do case 4 and then we will finish. Okay, so there are no questions. I'll go to the, we'll do the last case. No, case 4, which you can now guess that it leads to coexistence. Okay, so again I will draw the species 1 alkynes, n1 is equal to 0, and this, so this is k1, this is k1 by alpha 2 1, this one. So now this should be exactly opposite of this, right? So it came from above to below. Now let's just do the other way around. Okay, so this is, I think, at k2, this is k2 by alpha 1 2. Okay, and of course we have one more alkaline at n2 is equal to 0. So let's identify the equilibrium values. 1 at 0 0, 1 here, 1 here, and then we have a coexistence equilibrium. Okay, again, if you were to just do this, when both the species are high, they both will reduce. When both the species are low, they will both increase. So where will they go? Will they go here or will they go here? Let's look at this section here. In this section here, we are below the blue line, meaning n1 is still increasing, but we are above the red line, meaning n1 is declining. So net effect will be towards this equilibrium, away from this equilibrium and towards this equilibrium. Let's do the same thing in this region. In this region, I'm above n1, therefore n1 has to reduce. But I'm below the red line, meaning n2 is still increasing. So the net effect is, the net flow will be in this direction. So basically, this is the stable equilibrium and all the other three are unstable equilibrium. Okay, and what are the conditions for this? Conditions for this is K2 is less than K1 by alpha 2 1, which means that K1 is greater than alpha 2 1 K2. What does this mean? When the species 2 is fully on its own, even then species 1 can invade. That's what the first condition means. And now likewise, we need to have K1 has to be less than K2 divided by alpha 1 2. I have written down the condition for this part, x-axis condition here. This leads us to K2 is greater than alpha 1 2 K1, which means that even when you have a system with full species 1 at its carrying capacity, K2 can still invade, meaning both of them can mutually invade each other. Okay. What this means is that both species can mutually invade each other even when the other species is abundant. Consequently, what we find, coexistence is a stable equilibrium. Is it fine? Okay, I will stop here and we'll continue the discussion of this in the next class again with a quick revision. Let me know if you have any questions. Any questions?
So, in a way, when interspecific competition is greater than intraspecific competition, you will have you won't have stable coexistence. But if there's more intraspecific competition than interspecific competition, you have stable coexistence.
Can you just because your voice was slightly breaking to me? Can you basically you're saying comparing the intraspecific and the interspecific competition,
Yeah.
right? Yeah.
So basically, K1 would represent intraspecific competition, and alpha to 1, K2 would represent interspecific.
Absolutely. That's a very good point. I'm glad you said this. Yeah, absolutely right. You know, when intraspecific competition is dominant, then two species can coexist. And if the interspecific competition is dominant, then only one species can, and who will win depends on who has a stronger impact on the other. Absolutely true. Yeah, thanks for that interpretation. Maybe I'll also write that down because it was good. Can sort of interpret K1 as competition to species 1, right? And then alpha to 1, K2 as interspecific competition to species 1. So basically K1 greater than alpha to 1, K1 implies that intraspecific competition is dominant. And that's true in for both 1 and 2. Okay. And when that happens, both the species will coexist. Yeah. Anything else? Okay. So I think if there are no questions, we can close the class now. I'll see you all again on Friday.
Thank you.
Thank you. Bye.
Thank you.
Thank you, everyone. Bye. I hope it was not too fast today. Was it too much to absorb today? It's mostly graphs. If you go through it on your own, so it's very important that you just also do this exactly on your own. You will really understand what each term means and the interpretation of each coefficient. You will get a much better understanding of that if you do it on your own.
Thank you.